Well, hello. Tell us your name and tell us a little bit about your project.
Yes, my name is Clinton Davison, and I am one of the researchers involved in the Davisson-Germer experiment, which was a series of experiments that eventually confirmed the de Broglie hypothesis of the wave nature of electrons. So from about 1923 to 1927, we conducted a series of electron scattering experiments, and these were inspired by de Broglie's hypothesis that if light could have wave-like behavior, then why couldn't particles behave in a similar manner?
What were you guys trying to do or find?
So the original intention of our experiment was not to confirm the wave nature of electrons. That happened coincidentally with the experiments we were conducting. So the original intention of the experiment with my partner, Lester Germer, was that we wanted to study the surface of nickel. So we had designed and built a vacuum apparatus to direct the beam of electrons at the nickel surface so we could measure the different energies and behavior of the electrons as they scattered off the metal surface. So in 1921, while working at Bell Labs, I was studying electron bombardment and secondary electron emissions. So just studying their behavior, not necessarily the wave nature. And those experiments continued through 1925, but our experiment evolved as we became influenced by other ideas in the field of quantum physics, as that was, constantly being evolved. And so Walter Elaser's idea in the 1920s that matter could be investigated by scattering, similar to how X-ray wave nature behavior was proved through X-ray scattering on crystalline materials. He proposed that electron scattering experiments being scattered off of crystalline materials could show their wave nature in a similar way. So our experiment, that's what it did. We did electron scattering off of crystalline materials, and we applied Bragg's law, and that was one of the first applications of Bragg's law to particle waves.
So, what was your role in the project?
So I began my career at Bell Laboratories just researching the emissions of electrons from metals in the presence of heat. And throughout my career, I've always been fascinated with quantum mechanics and discoveries happening in the field. So I always kept tabs on the new work that was being done, and I've always been fascinated by the work of de Broglie and his ideas in quantum physics. And the wave-like nature of light, and his hypotheses, influenced me and what I wanted to study. So it influenced me to want to study the scattering behavior of electrons. So my role, was initiating the experiments that led to this profound discovery. And with the help of my partner, we were able to confirm de Broglie's hypothesis.
Who else was involved in the project?
So my partner in crime was Lester Germer. He worked at Bell Labs with me, and he was a Columbia graduate. We both worked on this series of experiments together to prove this fundamental theory that really changed quantum mechanics.
Where did the project or experiment occur?
So the experiments took place at the hub of technological advancement. So where I spent most of my career, at Bell Laboratories in New York, New York. So it was there that Germer and I performed our first demonstration of the wave-like behavior of elementary particles in 1927. And Bell Labs is a significant place. It has served as the birthplace of many technological and fundamental discoveries across all areas of science. So we were very, very proud to have worked there and had our experiment conducted there.
Tell us a little bit how you conducted the experiment.
So the basis of the experimental setup was we had a vacuum apparatus set up where we could measure the scattered electron energies, and the electrons were released from a heated tungsten filament that was accelerated by a voltage, and they striked the metal surface of the nickel. So the experiment was necessarily, if we go by steps, so you would heat up the tungsten filament, and the thermally excited electrons would be released, and then this electron beam would be fired and directed at the nickel's surface. And then you had a Faraday box, which was pretty much an electron detector, and it was mounted on an arc, so it could be rotated to observe the reflected electrons off of the metal surface at different angles and measure their angular dependence. So in our experiment, we discovered that peaks at certain angles showed the intensity of the scattered electron beam, and that diffraction pattern indicated that the electrons exhibited a wave behavior. And so the scattering of the electrons and their angular dependence could be interpreted by Bragg's law and determining the lattice spacing of the crystalline nickel. And using the application of Bragg's law with electron scattering together led to the discovery that electrons exhibit wave-like properties, and this influenced the world of physics.
What impact did your project have on the physics community?
So our experiments, the Davisson-Germer experiments, they show that electrons behave like waves by a diffraction pattern when they're scattered off the crystalline structure of nickel. So our experiments in 1927 proved with evidence one of the underlying principles of the evolving theory of quantum mechanics. So the confirmation of de Broglie's hypothesis of the wave nature of matter greatly impacted the physics community and how they went forth with, quantum physics today. And in 1937, I received and shared the Nobel Prize for Physics for the experimental discovery of the diffraction of electrons by crystals. So I continued my investigations of electron scattering and their behavior as waves, and then I contributed to the development of the electron microscope, which is a profound technological advancement being used today.
Well, Clinton, what other events were happening around the world at this time period?
The 1920s, wow. They were a busy decade in history. There was a lot that was going on. I know while I was in the lab that major shifts were happening across the country and throughout the world. So some of the more significant events that were just happening around the country and the world at that time was the 19th Amendment had been passed. Yay. And then, we were dealing with the new era after the end of World War I, the effects of that happening. And then, across the world you had a rise of fascism and communism occurring. The Communist Party of China was created, and then the Union of Soviet Socialist Republics was formed as well. And then one of my favorite and most notable technological advancements of the 1920s was when John Bard created the first working television system. And I can say I was very, very happy when that happened.
Well, Clinton, we just appreciate you spending time with us today to share a little bit about your experiment and the impact it had on the world. And from me and the Simpsons family, we just want to thank you very much for your time.
Yes, thank you for interviewing me, and I was glad I could share my story of the Davisson-Germer experiments.